Action! Hello, and welcome to the Trig Talk Show, the 24/7 help for all your trig needs. My name is Katie Lenagro, and it looks like we have tons of topics to cover today. Isn't that right, Brad?
That it is, Katie. My name is Brad Becker, and today we are talking about the unit circle, trig identities, equations and formulas, trig graphs, solving triangles, and vectors.
Wow, that's a ton of information to learn. But don't worry, with Brad and I as your teachers, you'll be acing your next trig test.
Yeah, first on the list is the unit circle. I'll let Katie start us off by introducing the most basic topic of trig.
Before we get started with the unit circle, I'd like to check your background knowledge on trig. We have sine not sin, please remember that, cosine, and tangent. Sine is opposite over hypotenuse. So in this triangle, sine of theta would be b, which is opposite of the angle, and the hypotenuse, which is always the longest side of the triangle. Cosine is adjacent over hypotenuse. So we look at the side that is adjacent to this angle, which is this one, and then the hypotenuse again. So cosine of theta for this triangle would be a over c. Tangent is opposite over adjacent. So opposite of theta is b, adjacent to theta is a. So tangent of theta is b over a. Just always remember, so, ka, toa. Recognize this? That's right, it's the unit circle. This concept is vital to your trig knowledge. As you can see, we have the degrees up to 360 because it's a circle. The basic pattern is 30 degrees, 45 degrees, 60 degrees, 90 degrees. So what you do is you add 30, then you add 15, then you add 15, then you add 30. And you do that all the way around the circle until you get to 360 degrees. The easy part is filling in the radians after that, because there's a simple formula to convert degrees to radians, as shown down here. You take x amount of degrees and multiply it by pi over 180 degrees. So as you can see, I have 90 over 1 times pi over 180. So you can cross these degrees out and simplify this, so it turns out to be pi over 2. And as you can see, right there, pi over 2. You can also reverse the formula if you ever need to convert radians to degrees. Right here, so you just do x amount of radians times 180 over pi. So you can see there's pi over 2 times 180 over pi. These cancel, these reduce, you get 90 degrees. Now we have the coordinates. The unit circle is in units of 1, so it's always over 1, up 1, over -1, or down -1. Then we have the coordinates for the different triangles. Always remember that for the triangles that are longer, it is root 3 over 2, 1/2. And then for the triangles that are taller, it's 1/2 root 3 over 2. You just flip it. The triangle in the middle is always root 2 over 2, root 2 over 2. When you go to the different quadrants, you also change the negatives. So in this quadrant, quadrant 1, everything is positive. In this quadrant, only the first number is negative. In the third quadrant, both numbers are negative, and in the fourth quadrant, only the second number is negative. And that's your unit circle. Our next segment with the unit circle are coterminal angles and reference angles. First, we have coterminal angles, which basically means you add 360 degrees or 2 pi to your angle. So if you had 300 degrees and you added 360 degrees to it, you would have 660 degrees, which is in fact a coterminal angle of 300 degrees. If you had pi and you added 2 pi to it, you'd get 3 pi, which is a coterminal angle of pi. Simple enough, right? Reference angles, or theta prime, are basically supplementary angles. So if we have 300 degrees, we know that from here all the way to here, because it's our unit circle, that's 300 degrees. Now, if you take from the closest horizontal axis to here, That's part of your supplementary angle. Then to find your other part, you look there. So that would be 60 degrees. So theta prime is 60 degrees. And one of the last things you need to learn with the unit circle is the arc length equation. So obviously r equals radius, theta is your central angle, and arc length is represented by s. So the equation is s equals r times pi, or arc length equals radius times theta. You have to remember this equation is always in radians. Do not try to do this with degrees, ever. So let's take this example. Our radius equals 5 and theta is 210 degrees. What did we just learn? It can't be in degrees. We have to change it to radians now. So 210 in radians is 7 pi over 6, and we know that from the unit circle. So s equals 5 times 7 pi over 6, which equals 35 pi over 6.
Alright, so here we have a pretty simple problem representing linear speed. So what we're trying to figure out is how fast this bandsaw is moving. So we know that it has a radius of 7 inches, and it can make one full rotation in 0.2 seconds. So that's pretty fast. Now what we need to do is find this overlying question of what is the linear speed of the blades going past this little section. So we know that the circumference of this entire thing equals 2 pi times radius, which means since our radius is 7 inches, we now have the formula c equals 2 pi times 7, which can be simplified to c equals 14 pi. Now, we know one rotation is 14 pi inches per 0.2 seconds. And when we do all the math there, we get 219.9 inches per second is how fast this is moving.
Wow, Brad, you really learned a lot, didn't you? Do you think you could show me some important trig identities and formulas? I really want to know how to solve and verify trig equations.
Sure thing, Katie. So today we're going to be going over all of the properties, identities, and everything else that you could possibly imagine for trig equations. So first, we have the Pythagorean identities. The most basic one is sine squared theta plus cosine squared theta equals 1. Next, from that, we can get 1 plus tangent squared theta equals secant squared theta. And another one, 1 plus cotangent squared theta equals cosecant squared theta. After that, we can go into reciprocal identities. So these are finding the relationships between all of the sines, cosines, cotangents, tangents, cosecants, and secants. So sine of theta equals 1 over cosecant of theta. Cosecant of theta then is 1 over sine of theta. This goes for all the other identities, as cosine of theta equals 1 over secant of theta, and secant of theta equals 1 over cosine of theta. And finally, tangent of theta equals 1 over cotangent of theta, and cotangent of theta equals 1 over tangent of theta. On the bottom of the board here, I have the quotient identities. These are saying the relationships between sines and cosines and tangents. So, to begin, tangent equals sine theta over cosine theta, as well as cotangent goes for cosine theta over sine theta. Alright, so I've got another board here. To continue with cofunction identities and even odd properties. So in cofunction identities, it's where we learn the relationships between sines and cosines, especially in graphing. So sine of theta equals cosine of theta minus pi over 2. And cosine of theta equals sine of theta minus pi over 2. Tangent of theta equals cotangent of theta minus pi over 2. So we can see a trend here that in each one, it's similar to the other in the fact that you have to subtract pi over 2 from theta. Alright, under even odd properties, we have some pretty simple stuff going on. So our even property is cosine of negative theta equals regular cosine of theta. So nothing too interesting, you're basically just dropping the negative. Under our odd properties, we have sine of negative theta equals negative sine of theta, as well as tangent of negative theta equals negative tangent of theta. Alright, so now we're going to talk about verifying some of these identities. So let's take the Pythagorean identity for example. So we have sine squared theta plus cosine squared theta equals 1. Now we're trying to transform this into something we know, which is 1 plus tangent theta squared, or tangent squared theta, pardon me, equals secant squared theta. Now, what we can do is let's take the entire thing and do nothing to it by dividing everything by cosine squared theta. So this is just a way to look at it differently. So we now have sine squared theta divided by cosine squared theta. Now, this is a quotient identity, so we can take this and make it tangent squared theta. Cosine squared theta divided by cosine squared theta is just 1, so that's pretty simple. And then we have 1 divided by cosine squared theta is a reciprocal identity, which means that it's secant of theta, secant squared theta. So we just transformed the Pythagorean identity into another Pythagorean identity by doing something simple. And that can be applied in the same way with sine squared theta. So if we take sine squared theta divided by sine squared theta, it's 1. Now, cosine squared theta divided by sine squared theta is a quotient identity, which means that it will become cotangent squared theta. And we have a reciprocal identity, which is 1 divided by sine squared theta equals cosecant squared theta. Now, we can take all of this and apply it in an application problem. So let's say we're trying to solve it now. So we have 1 plus tangent squared theta equals secant squared theta, and our ultimate goal is to find cosine of theta. We know that tangent squared theta, just for instance, equals 1. So we can apply that into here and have 1 plus 1 equals secant squared theta. This can be simplified to 2 equals, and then now using a reciprocal identity, 1 over cosine squared theta. So that we can now get cosines in the equation. From here, we have cosine squared theta equals 1 divided by 2 they equal each other. So to simplify this, we can take the square root of cosine squared theta, since we're trying to get cosine theta, and take the square root of 1/2, which means that we now have root of 1, which is just 1, over the square root of 2, which if we multiply it by a fancy 1, which we can call square root of 2, divided by square root of 2, we can now get square root of 2 over 2 equals cosine.
This is called rationalizing the denominator.
Yes, it is. Alright, thank you. Okay.
Here we have the sum and difference formulas. Make sure you have these written down somewhere because they are very important for trig equations. Here are power reducing formulas. Here are the product to sum formulas. Here are the sum to product formulas. Here are the half angle formulas. And last, here are the double angle formulas.
Alright, so now we're going to talk about the use and application of some of the formulas. So I picked sum and difference formula, which is pretty simple, pretty good to use. So let's say you have a problem that you have 45 degrees, which could be u, and v is 30 degrees, obviously goes there. So your original formula is sine of u plus v equals sine of u times the cosine of v plus cosine of u times the sine of v. So when we plug in our u and v values, which is a new formula, which is sine of 45 plus 30 degrees, gives us sine of 45 degrees times the cosine of 30 degrees plus the cosine of 45 degrees times the sine of 30 degrees. Now, you may be wondering why we don't just add these together to give the sine of 75 degrees. Well, off the top of our head, we don't really know what the sine of 75 degrees is. So in this case, it's easier for us to break it up. Since we know that the sine of 45 degrees is root 2 over 2 times the cosine of 30 degrees, which is root 3 over 3, plus the cosine of 45 degrees, which is the root 2 over 2, times the sine of 30 degrees, which is 1/2. Now, when we simplify these down, we can get root 6 over 4. And we can add that to our other ones, which is root 2 over 2 times 1/2, which happens to be root 2 over 4. So when we add these together, since we have a common denominator, we can just get root 6 plus root 2 over 4 is the sine of 45 degrees plus 30 degrees. 1.
Golly, Brad, you know so much about trig.
I like to think that I'm pretty good at trig. One thing that I do want to learn more about, though, is graphing trig equations.
Well, today's your lucky day.
Oh, good.
In this next segment, we're going to learn about graphing trig equations. Right here, we have a basic equation for a sine graph. So it's f of x equals a times the sine of b of x, b times x minus c plus d. So the a in this equation is the amplitude, which means, you know, the height, basically. B in this equation is the period. C is whether the equation is shifted left or right. And D is whether the equation is shifted up or down. You can also have this with cosine too. So to find the amplitude, it is just the absolute value of A. Did it just turn off?
It's fine.
Oh, B equals B, which is the period. We also call it T, which equals 2 pi over B. So if B was 1, then it'd be 2 pi over 1, and that would be the period. The scale is the period divided by 4. So if the period is 2 pi, you divide it by 4, the scale would be pi over 2. And if you have a phase shift, that would be C divided by B. Okay, so this is your basic sine graph. When it's just in this basic form, it always goes through the origin. So the amplitude of this graph is 1 because the highest point is 1, the lowest point is negative 1. The period is 2 pi. As you can see here, from the start to 2 pi, that one little section right here is 1 period. We did the scale at pi over 2, so just every little section is a multiple of pi over 2. And because there is no C or B, this is negated. You don't even need to worry about it. Here is your basic cosine graph. So when it's in this simple form, it always is at its highest point at 0. So 1 period of this looks just like this. The amplitude is 1 because the highest point is 1, the lowest point is negative 1. The period is 2 pi, as you can see there. The scale is pi over 2, so every part of the graph goes through one of those points, which is a multiple of pi over 2. And because there is no C or B again, this is negated and you don't even need to worry about it. So those are your basic cosine and sine graphs. The next graph we're going to learn about is the tangent graph. So we're looking at y equals tangent of x. So as you can see here, they're basically just these little lines going all the way up or down because the range is negative infinity to infinity. It also goes through the origin, remember that. And these dotted lines represent the asymptotes because the domain is all real numbers except for pi over 2 and any multiple of pi after that. So the domain, the period, the period is always pi because of the asymptotes. And so that's basically your tangent graph.
Well, by gosh, Katie, you certainly make graphing trig equations look easy.
Well, as long as you remember the important points, it is easy. For me, law of sines is one of the most helpful parts of trig. So basically, you take a triangle like this, and your angle A, the side A is always opposite of it. So you know, angle C, side C is always opposite, and same with B. So it goes like this. A over sine of A is equal to B over sine of B is equal to C over sine of C. So if we take this example where A is 38 degrees and B is 62 degrees and A is 7. So we do 7 over sine of 38 equals B over sine of 62. And you do the normal proportion, so 7 times 62 divided by sine of 62 divided by sine of 38 equals B, which is 10.04. So you can fill that in, and then you add up the angles, and you get 100. And so 180 minus 100 is 80. So that is your angle measure for C. So now you can do 7 divided by sine of 38 equals c over sine of 80. And you do the same proportion thing, so 7 times sine of 80 divided by sine of 38 equals c. And c is 11.20 if you round it. And there you go. You have all three sides and all three angles. See how simple it is to solve a triangle with the law of sines?
Next up, we have the law of cosines. Using the law of cosines and the law of sines combined can help you solve any triangle. So, we have, to start off with a normal triangle. Law of cosines is applied in this case, when you have two sides and one angle adjacent to the two sides. And this is when you can't use the law of sines, since you don't know the ratios here to here. So, we get a formula from this saying side A equals b squared plus c squared minus 2bc cosine of angle A. From here, let's do an example to show you how this all works out. So, solve the following triangle, hypothetical triangle. Given that angle A equals 30 degrees, side B is 7, and C is 10. So, we get our basic triangle set up, and we plug all these numbers into our formula. A equals 7 squared plus 10 squared minus 2 times 7 times 10 cosine of 30 degrees. We can simplify that down to A equals 49 plus 100 minus 140 cosine of 30 degrees, or A equals 149 minus 140 root 3 over 2, which equals 140 minus 121.24, and this equals 27.75, which equals A. So we have this right up here in our whole solving. Angle A equals 30 degrees, so side A equals 27.75. Now, to solve the rest of the triangle, we can go back to the law of sines. So we find the relationship between the sine of angle A and the length of side A. And we can set that equal to, let's just say C. So we know that side C is 10, and we're trying to find the sine of C. So we can get a formula that says the inverse sine of 10 sine of 30 degrees divided by 27.75 equals C degrees. And now that we know what angle C and angle A are, we can subtract both of those from 180 degrees to get B, which happens to be 139.62 degrees. So there's our triangle.
Next we're going to learn about how to find the area of a triangle with two sides and an angle opposite of those sides. So we have three formulas just for the different combinations that you can have. So the first is area equals 1/2 of B times C times the sine of A. Or you can have area equals 1/2 of A times B times the sine of C. Or you can have area equals 1/2 of A times C times the sine of B. Let's look at this example. So we have two sides and an angle. So we set up the problem like this. Area equals 1/2 of 20 times 15 times sine of 37. Which simplifies down to area equals 150 sine times 37. And the answer is area equals 90 times 90.27.
Another thing that can be helpful when solving equations and triangles for area is using Heron's formula. Heron's formula can be used when you have three sides of a triangle. And in Heron's formula, we use a variable that we call S. And S equals side A plus side B plus side C, all divided by 2. Now we plug this into the equation, which area of any triangle is the square root of S times S minus A times S minus B times S minus C. Well, solving triangles using the law of sines and cosines is the easiest part of trig.
And now we're going to introduce what I think is the most difficult part of trig, vectors.
Well, that's where you're wrong, Katie. I can show you just how simple vectors can be. Alright, so here we have vectors. Vectors are simply line segments with direction and magnitude. Direction being the direction from the initial point to the terminal point, and the magnitude basically being the length. So a vector in standard position is its initial point is at the origin, like these. Now, direction of a vector in graphing especially is slope. So that's pretty easy to remember. Magnitude can be found using the distance formula. And the distance formula is the square root of x squared minus, or x2 minus x1 squared plus y2 minus y1 squared. And the initial point would be x1, y1, and the terminal point would be x2, y2. Now, the component form of a vector is v1, comma v2. Or if it's not centered at the origin, then, or if its initial point is not at the origin, then it would be represented by q1 minus p1, q2 minus p2. Now, in linear combination, it's kind of taking this and making it more readable and usable. So, we're going to have I represent 1, 0, and j is 0, 1. And this represents a vector v1, v2 can be the vector of 1, 0 plus vector of plus v2 of 0, 1 equals then v1 of I plus v2 of j, since this comes from here and this comes from here. In direction angles, it's basically we take the unit vector, so we should actually learn about the unit vector first. The unit vector represents the vector with a magnitude of 1, which is centered at the origin, which would mean that it basically has a terminal point on the unit circle. So now going back to direction angles, the direction of the unit vector v of theta to the terminal point on the unit circle is basically what it is. So it's saying that from the origin to the point on the unit circle is a certain amount of degrees. So let's say 30 degrees or something like that. Pretty simple. It can be represented by xy or cosine theta, sine theta, you know, from the component form that we have up here, or if we want to see it in with a linear combination, cosine of theta I plus sine of theta j. Alright, so now what we're going to do is learn about addition and multiplication with vectors. So let's say you have a vector u plus vector v. And we can see here that this is u, this is vector u, and this is vector v. Now, we're going to take this and it'll become u1 plus v1, comma, u2 plus v2. So, what it'll end up looking like after all of that is this orange arrow here, which is, or this orange vector, which is vector u plus v. So pretty simple. Now multiplication affects everything on the inside, all the vertical and horizontal components of it. So if you have 2u plus 3v, for example, then your component form would look like 2u1 plus 3v1, comma 2u2 plus 3v2. Alright, now that we have all this, let's apply some of this. So we have a problem. Let's say a plane is traveling up and out a distance of 50 and up 80 kilometers. At this point, it switches and levels out and goes a distance without changing altitude for 100 kilometers. Now, from here, we're trying to find the distance from its initial takeoff to where it is now. To do this, we take our first vector, let's say vector u, would be 50, 80. So 50 kilometers in the horizontal component and 80 in the vertical. And vector v, which has 100 kilometers in the horizontal but 0 in the vertical. So when we combine these, we get vector u plus v is 150 kilometers, 80 kilometers. So from here, all the way to here, it's 150, and from here up and out would be 80 kilometers.
Wow, Brad, you were just amazing at math.
Well, thanks, Kitty. You as well, by the way. And, well, that's all for now, folks. Join us next time with Algebra Atrocity.